In this video, we'll take a look at a few important properties that deal with symmetric and orthonormal matrices. One that we recall from earlier on is that the transpose of any product, so if you take A times B and then you transpose that product, that you get B transpose times A transpose. In other words, to calculate the transpose of a product, you could transpose the individual matrices and then multiply them in reverse order. But why reverse order? Well, let's suppose that A is an M by N matrix, and let's suppose that B is an N by P matrix. So M by N times an N by P, since the inner dimensions match, will produce an M by P matrix. And if you transpose an M by P matrix, you'll get a P by M matrix. We have to remember that the transpose of a matrix is turning the columns of the matrix into the rows of the new matrix. So for instance, if I have 1, 2, 3, 4, 5, 6, and I want the transpose of that, I'm going to turn the first column into the first row of this transposed matrix, and then the second column will become the second row of that transposed matrix. So notice that what we started with here is a 3 by 2 matrix and ended up with a 2 by 3 matrix. So an M by P matrix, when it gets transposed, will produce a P by M matrix. Now, our justification, or at least our reasoning for why this will work out, is that means B transpose would be a P by N matrix. A transpose would be an N by M matrix. And since now the inner dimensions match, we end up with a P by M matrix. If you were to try to multiply A transpose times B transpose under these conditions, A transpose is N by M, B transpose is P by N, but these do not match, and therefore that product is not necessarily possible. So this is just our justification for why this theorem is true. Now, we've not taken a look at symmetric matrices yet, but a symmetric matrix is just a special type of matrix in which it is the case that when you transpose it, you end up with exactly the same matrix you started with. The symmetry occurs with respect to the diagonal. So in this case, this is a diagonal matrix because if you look at, or a symmetric matrix, because if you were to put a strike through the diagonal, you can kind of see the symmetry of the 2, 3, 6 here and the 2, 3, 6 here. So it's as if we were to fold over the top triangle and we would get exactly that bottom triangle. Now, if I attempt to transpose this, 1, 2, 3, 2, 4, 6, 3, 6, 8, if I transpose this, then by the definition of a transpose, the first column becomes the first row of our transposed matrix. Our second column becomes the second row. And the third column becomes the third row. You can see that that is exactly the same matrix we started with. 1, 2, 3, 2, 4, 6, 3, 6, 8. And so this is equal to our original matrix. When we transposed A, we ended up with exactly the same matrix that we started with. Now, the reason we like symmetric matrices is because they have a special property. Symmetric, and we'll consider this to be a theorem. We're not going to prove this here, but we'll take a look at an example. Symmetric matrices have an orthogonal basis of eigenvectors, meaning that you'll get if you had a 3 by 3 matrix, you would get a basis, meaning that you get a set of vectors that span the space in which the rows and columns of that matrix exist in. So a 3 by 3 matrix would have a 3 by 3 symmetric matrix would have 3 linearly independent eigenvectors. And how do we know they're linearly independent? Well, they are orthonormal, or rather orthogonal. We can make them orthonormal by multiplying by the reciprocal of their magnitude, in other words, dividing each eigenvector by its magnitude. We could make them unit length, but they will be orthogonal to begin with. So an n by n matrix that's symmetric will end up with n linearly independent eigenvectors. Again, they're going to be orthogonal, and we can make them orthonormal pretty simply. In this case, here's our matrix. I have the output of the eigenvectors. Now these are in approximate form, but if I take to verify they're orthogonal, recall that orthogonal vectors x and y satisfy the property that x transpose, or rather, I won't even put a transpose there, I'll just say the dot product between x and y is equal to 0. So that's the way I could check, and let's just go ahead and verify with perhaps these last two, since I kind of like the way V3 looks. So to take the dot product, and I'm going to approximate this is about negative 0.56, negative 1.12, and 1. And if I dot that with negative 2, 1, and 0, I'll get negative 2 times negative 0.56, which is which comes out to 1.12. Plus, in this case, I'll get 1 times negative 1.12, which is negative 1.12, and 0 times 1 is 0, and in this case, even our approximation gives us a dot product of 0. So we can see that they are orthogonal. We'd of course have to show it for this pair and then for the first and third vectors as well, but that is something that you can certainly do if you'd like to verify that. Now, the really cool and powerful thing that's going to help a lot in image compression is that even though images themselves are often not square, we can take a matrix and its transpose and multiply them together, and we end up with a symmetric matrix. So what would that mean? How do we know A transpose A transpose multiplied by A? By the way, if A is, say, M by N, it's not a square matrix, then if you multiply A transpose with A, first of all, let's verify that they're going to be square matrices. Well, A transpose would be N by M. A is M by N. Inner dimensions match. You'll end up with an N by N matrix, which is square. So we can't have a symmetric matrix unless it's a square matrix, because if it's not a square matrix, then the transpose will have a different number of rows than the number of columns. And here we have an M by N matrix multiplying an N by M matrix, inner dimensions match. In this case, we end up with a different sized square matrix, but it is still square. So how do we know that these are symmetric? Well, in order to prove that they're symmetric, it must be the case that the transpose of a matrix is equal to the original matrix. So for instance, if I look at case 1, if I take A transpose A and I transpose it, I should still end up with A transpose A if it's symmetric. Well, by properties of transpose, since this is a product, the transpose of a product is the product of the matrices transformed in reverse order. So here I'll have the second matrix, A transposed, multiplied by A transpose transposed. Well, if I transpose a transpose, if you change the columns to rows and then you change them again, then you end up with exactly A. If you transpose a matrix twice, you get what you started with. And this is going to give me A transpose A, which is exactly the same matrix I started with before I transposed it. Same kind of notion goes for A transpose. If I take the transpose of that, well, in that case, it'll just be the second matrix transposed multiplied by the first matrix transposed. And again, A transpose transpose is A times A transpose, and we see that we get exactly what we started with. Very cool stuff. That's going to be very, very powerful, because not only can we make a square matrix out of an image, but we can also make a symmetric symmetric matrix out of a non-square image. And the very last theorem that we'll look at here is that if Q is an orthonormal matrix, then its inverse is equal to its transpose. If Q is an orthonormal matrix, then the inverse of Q is equal to its transpose. Now this is fascinating because if you have an orthonormal matrix, then this is saying that you don't have to do any work to find, well, any significant work to find its inverse. All you have to do is transpose it and you have the inverse of that matrix. Let's go ahead and take a look at an example. In our most simple example, let's take a look at a 2 by 2 matrix that I'm going to claim is orthonormal. And let's recall what that means. To be an orthonormal matrix, there are two properties that must be satisfied. The columns are orthogonal. That means that if I call the vectors of that matrix Q1 and Q2, that's going to mean that their dot product is going to equal 0. And also, the columns are unit length. And so what that means is that the length of Q1, or the magnitude of Q1, is equal to 1, and the magnitude of Q2 is also equal to 1. So we can verify that. We can see that the columns are orthogonal. If I take the dot product between 1 over the square root of 2 and 1 over the square root of 2, and I dot that with negative 1 over the square root of 2 and 1 over the square root of 2, then I end up with negative 1 times 1 over the square root of 2 times the square root of 2 is negative 1/2. And here I'll have 1 square root 2 times 1 over square root 2, which is plus 1/2, which equals 0. So that satisfies the first condition. And the second condition is that I have to check that the length or the magnitude of each of these vectors is equal to 1. So Q1 is the square root of the sum of the components squared. And that's going to equal the square root of 1/2 plus 1/2. And 1/2 plus 1/2 is 1. So we end up with the square root of 1, which is 1. Q2 will be a similar approach, right? Except one of them will be negative 1 over the square root of 2. And that gets squared, so that still gives me positive 1/2. And then 1 over the square root of 2 squared. And that's going to equal 1 as well. So condition 2 is satisfied as well. Now to show that the product of their transpose, Q with Q transpose, for example, Q times Q transpose is going to be 1 over the square root of 2, 1 over the square root of 2. So here I have it. I've transposed this column into this row and this column into this row. And now when I compute the product of these matrices, I'll have 1 over the square root of 2 times this column plus negative 1 over square root of 2 times this column. And I'll just quickly write that out. Here I will get 1 over the square root of 2 times 1 over the square root of 2 is 1/2. And then here I'll have the negative times a negative, which will be positive 1/2. And 1/2 plus 1/2 is 1. Here I'll get 1 over the square root of 2 times 1 over the square root of 2, and negative 1 over square root of 2 times positive 1 over square root of 2, which will give me 0. And similar kind of idea holds here. I'll get 0 and 1. And so that's equal to the identity matrix. And at least for this case, we see that since I take Q and multiply it by its transpose, I get the identity. And so the other thing to check is that Q transpose times Q, that will also give us the identity matrix. Now you can verify that. And what this concludes is that Q transpose is the inverse matrix of Q. Why is that the case? Well, because any matrix that when multiplied by another matrix that produces the identity in both orders is considered to be the inverse matrix. So that's an example of multiplying an orthonormal matrix by its transpose and seeing that the transpose is the inverse.